Hello, Calc. You're watching this video after Thursday's class, which is Groundhog's Day. By now you'll know whether the groundhog saw its shadow, although 6 more weeks of this mild winter would be nothing to talk about. So we'll see what happens. And you'll be seeing we don't meet on Friday because of the pastor's breakfast, so we have a chance to watch this video after class on Thursday or on Friday or on Saturday or on Sunday, sometime before Monday, please. Derivatives involving absolute value. Here we go. All right. To understand this, I'm going to talk about it mathematically, and then I'll talk about it the way I think about it. So one of those ways will prove helpful to you. I want to start by a discussion of this, the cube root of 8. And you'll see where this ties in, so hang in there. The cube root of 8 is what number times itself times itself. So you have it use it a factor 3 times will give you 8. So since 2 times 2 times 2 is 8, we know that the cube root of 8 is 2. So that's okay when this is odd. And if we put in a negative 8, it has no ambiguity because there is a number that multiplies times itself as used as a factor 3 times will give you minus 8. And that's negative 2 because negative 2 times negative 2 times negative 2 is negative 2. So when this is odd, we're fine. However, when this is even, we find that we do have some ambiguity. Let's talk about the square root. Another way, before we leave negative 8 though, we can think of it another way as the cube root of negative 2 cubed. Because that negative 2 cubed can take the place of minus 8, and the cube root, it remains. So this we can think of in some ways even more easily than this, because this cube root undoes this cube and it leaves minus 2. So either way you think about it, we get minus 2. But when we go to the square root, or roots that are even, I don't normally write the 2, but I'm emphasizing that we're dealing with square roots. What would be the square root of minus 2 squared? So look what happens. If I work inside the radical first and square the negative 2, I end up with the square root of 4, which is positive 2. But if I apply this principle here, where the square root undoes the square and leaves what's inside, that way we get a negative 2. So the mathematicians had to decide which one it's going to be. So we're going, by definition, they decided that this answer was correct, and this answer was not. So by definition, the nth root of a to the n will equal a if n is odd. No problemo when n is odd. A if n is odd. But it's going to have to equal the absolute value of a. We're going to drop that negative case if n is even. So that's the way it has come down the corridors of math history to us. So let's use it. Let's use it or lose it. So we are going to look at this. Because of this definition, I'll work over here with this in view. We can say the absolute value of x can be rewritten as the square root of x squared. So we can do that. Yes, we can. It's kind of a weird connection here. You may not have seen that previously, but everyone in higher math knows that. And if we want to replace absolute value, it's sometimes confusing to work with. This sometimes becomes a plausible option. So we're going to use that plausible option. So we get, I'll rewrite our All right, I'll rewrite our key here. So the key, this is the key to the city right here today. Here's the key. All right, let's use the key by doing a problem. Say we have the absolute value of 2x minus 3 plus 1, and we want to find the derivative. All right, so let's rewrite this using this definition. So the problem can be rewritten without absolute values as a square root of what's inside the absolute value squared, plus 1. And now I'll go ahead and take the derivative because I'm familiar with square roots. So I'll rewrite that as 2x minus 3 squared to the 1/2. So it's easier to take the derivative. All right, so I will begin my derivatives by going from left to right across the expression, and when I get this first one, I know that I have something to the 1/2. So the 1/2 runs down in front, the something is repeated, and that exponent reduces by 1, and the derivative of 1 is 0. So I write nothing for that. So, oh, I forgot the chain rule. So before I did that, the 1/2 runs down in front, the something is repeated to the negative 1/2, followed by the derivative of the something in here. So the derivative of that is going to be 2 times 2x minus 3 raised to the now 1 times the derivative of that. Chain rule twice, or was it 3 times? All right, who's counting? All right, with that, I want to simplify that in a way that is useful to me. I can see this 1/2 will take away one of the 2's, and I could raise this to this, but I'm going to choose not to. I'm going to choose to write this expression in the denominator under the square root. So this is going to come downstairs and be in the square root. And that square root is 1/2, so it's the square root. And on inside we have 2x minus 3 squared. I prefer that, sorry. So I can rewrite this because it's a negative exponent. It goes into the denominator and it's a square root. So I want to leave, I could have raised this to this, that's one way to simplify, but it's not taking me in the direction that the key would. So I need a key here. So what's left in the top? Over here we have a 2 and a 2x minus 3, which I'm going to leave factored as well. So do you recognize what that expression tells me in regards to the original problem? Well, 2x minus 3 is what was in the radical. So that was, we'll call it u. Say 2x minus 3 is an expression in x. So it repeated, and it is in the numerator. And this 2 is the derivative of u. So it's going to be followed by du dx. And in the bottom, we have, this is the definition of, looking back here, we can write this as simply the absolute value of u. All right, so we have basically taken this example and developed a principle, and that's not a very rigorous proof, but it is true that the absolute, when we have y equals some expression u, let me gather our conclusion here. If y equals u, then y prime equals that expression, I'm sorry, if y equals the absolute value of u, then that expression, because that's what we started with, this part right here, with the derivative is going to be u, the expression inside the absolute value without the absolute value sign, divided by the absolute value of u times du dx. So when our expression is about greater than 0, this is just a 1. And when our expression is less than 0, this is just, this will be negative, and this will be positive always. That will be -1. So I think of it, this can be a way to do all your proofs with absolute, not proofs, all your problems with absolute value. But let me show you how I think of them a lot of times. All right, but before I do that, let me give you an example. So let's say that we have y equals the absolute value of sine x. And so what that means is, from our definition, or from our derivative box here, y prime is going to be the expression in the absolute value divided by the expression in with the absolute value times the derivative of the expression, which in our case is cosine x. And that's your answer. So you can see when sine is positive, this is just cosine x. When sine is negative, the answer is negative. This will be a -1, and that'll be negative cosine x. Let's see why that actually makes some sense. Wouldn't that be nice? All right. So here's why you end up with a plus or a minus the derivative of the expression. And again, this is how I more often think of it, although that expression is fine. Suppose we have y equals 2x minus 2. So that's a straight line. It crosses the y-axis at -2, and it has a slope of 2. So I'll rise 2 and run 1 to get another point on. So we have this line, and I'm wondering how that changes when I put absolute value signs around the expression. Well, this is always positive, absolute value, so what happens to all these negative values? They flip up, so this reflects across the x-axis, and this part goes up here. So that one's no longer there. It's been reflected across the x-axis. And notice the absolute value function. It has a positive part when f of x, the y values, are positive. The derivative is just the same as it is of 2x minus 2. But on this side, when f of x was negative, then the derivative becomes the actual negative value. So suppose the derivative of this is 2, which it is, then the derivative of this is -2. So it's the same, but the sign is different. The slope is positive here, negative here. So is the derivative. All right. So I keep that in mind. So what about the one that we just did? We're looking at absolute value of sine x, like that. And the derivative of that will follow this picture. We already did the work, so I won't repeat it. So here's the sine function. It starts here, goes like that. All right, so that's 2 pi right there, and goes forever like that. So what does the function look like when I put the absolute value sign around it? So whatever's negative reflects across the x-axis. So this goes away and it comes up here, and this would go away and come up here. So everything would be above board, above the x-axis. So I can see then that if I knew the derivative of the regular sine curve, when it's above the x-axis, then the derivative is the same. It's cosine x. But when we're looking at a value that would be below the y-axis, the x-axis, so it have a negative y value, then we know that it's going to be the same as that slope, but in the opposite direction. So when f of x is negative for a sine function, the absolute value takes on the opposite way. So the slope down here would have been negative, but the slope of the absolute value function is the same value numerically, but the positive sign. That helps me mind muscle through problems where the definition does not. And I'll end with just a discussion is sometimes our absolute value signs fall within the function and not the entire function. So say we have f of absolute value of x. So notice that is different from the whole function being in the absolute value. So we just talked about that. What about when the absolute value is inside the f function? For example, we could have y equals e to the x, and then we could say just y equals e to the absolute value of x. So do you see this whole function is not in the absolute value, but the expression, the x expression is. So here's how I think of it, and should you come upon it in your mathematical wanderings, I think it might be helpful. Here's what e to the x is. You've been well taught. There's a tail. It crosses at 0, 1, and then goes zinging up. So every exponential does, so does e to the x. When this happens, notice the function on this side will never be chosen. Because you won't. This is y equals e to the x. And it will never come out to play that x, say x is minus 1. So if I put a minus 1 in this function, I get e to the absolute value of minus 1, which puts me over here again. So therefore, this tail can be dropped. Anything to the left can be dropped. And then this function becomes a mirror of this. So this reflects across the y-axis, and that's what's going on here. So let me show you in a more theoretical one. I guess I can do what I do then. Let me go and finish this one before I ditch it. So I redefine this without the absolute value. I take a gander at it. It will always follow this principle. The left part to the left of the y-axis will disappear, and it will take on the reflection from whatever is on this side of the y-axis. So let me redefine that without absolute value. So this function y, when x is greater than 0, it looks normal. It's y equals e to the x. But when x is negative, then it takes on this function, but it's going to recall how we can write that. We learned that when you reflect across the y-axis, the exponent takes on a negative value. All right, so then if I use these pieces, I could find the derivative of that. So let's do y prime now. So y prime is going to be the derivative of that. I'll write it in the normal order. When x is, and I'll say greater than or equal to, when x is greater than or equal to 0, the derivative of that is just e to the x. But when x is less than 0, you take the derivative of that. So the derivative of e to the minus x is e to the minus x times minus 1. So we get minus e to the minus x. So a good way to deal with it, when the absolute values are within the function, think of what it's doing. Redefine the function without absolute value, and then do the derivative of each piece. So theoretically, this is what we have. Suppose we have some function that looks like this. It goes All right, so we have that function. So that's y equals some function. And now let me discuss y equals the function where the x expression within the function is in absolute values. So now this part will never come out to play, because whatever I put a negative number, it turns to a positive number. So the values over here are going to take on the same values as they did over here. So I'm going to reflect this across that x-axis. I'm going to try to draw the same thing. Good luck. There. Alright, I'm trying to make this a mirror image of that. Alright, that's what happens with absolute values. And I know it can be confusing, so maybe as we do some problems, those confusions will disappear, like melting snow. Alright, I forget what melting snow looks like though. Alright, that's it for this discussion on derivatives involving absolute value. See you later.